up until this point, we have calculated enthalpies of total reactions, right? We've looked at what's the energy change for the total reaction, okay? And we used Hess's law to look at mini reactions to figure out the steps in which a reaction takes place. But so far, we've looked at enthalpies of total reaction, right? Change in energy of a total reaction. But now we're going to look at change in enthalpy about one compound, okay? We're going to look at the change in energy of the formation of a single compound. And so that's called the enthalpy of formation. We're going to look at what's the energy change that happens when 1 mole of a compound is formed, okay? So when we look at the enthalpy of formation, we're looking at a mole of compound from its elements with all substances in their standard states, okay? So when we talk about standard states, we're going to talk about what are they normally a solid, a liquid, a gas, and then the formation that's going to cause that to become a compound. Because really, in later chapters, we're going to look at all the steps that it takes 2 ions to become a compound, right? They've got to go into a certain state of matter. They've got to do all of this stuff. But right now, we're looking at big picture of that, okay? How much energy does it take for a compound to be formed, okay? The really important part of this, and that's why I made it red and bold and italicized, is that we're looking at 1 mole of the compound. So not all of the time will our reaction call for 1 mole of the compound, right? But our enthalpy of formation, the values that are given to you on that table right there, those all represent the enthalpy change when we form 1 mole of the compound. So that's really important, okay? This says, this symbol right here, what's that triangle mean? Change in, what's the name for it though? Delta, right? Delta H, and the little F stands for delta H of formation. Indicates that the reaction has taken place under standard conditions, right? Can anyone, for bonus points here, tell me what is standard conditions?
Oh.
It's 273
273 Kelvin, 1 atmosphere. Good. Okay. All right, good. All right. We are going to look at... I skipped one here. Okay. Here we go. No, stop. All right. We want to calculate the delta H for the following reaction. I gave you the information here, but we can check that these values match the values in your table. Why don't you look at these values and make sure they match the values in your table? Okay, what's the heat of formation or enthalpy of formation for sodium? And make sure you look at sodium solid. I want you to look on your table. Is it on there? Did I speak too soon? No, it's on there. Okay, we're looking at the first column right there, right? It's 0, right? Because sodium's standard state is 0, so it doesn't take any energy for me to get to a solid, right? Because that's what its standard state is. Does that kind of make sense? Okay, H2O as a liquid, right? So here's when states of matter actually do make a difference, right? We choose to ignore them pretty often, but it does make a difference here. The liquid water is a negative 286 kilojoules per mole. Sodium hydroxide is negative 470. And then why is H2 a 0? Why is hydrogen gas a 0? How does hydrogen normally exist? As a gas and as a diatomic. Good. It has to exist as a diatomic. So there's no energy that was required to form that because that's its natural or standard state, right? It wants to be in that formation. So, okay, ignore our answer right here for just a second. Let's figure out how do we get there, okay? We've got to know that these values given to us, okay, the values given to us here in our table are for the formation of that compound. The formation of the compound. And so if the compound is on the reactants side, that's not the formation side, right? That's what's being broken down. And so if it's on the reactant side, what has to happen to it? Take a guess. What do we have to do with Hess's law? If we had to reverse the reaction, what do we have to do? We had to change the sign. The same thing happens here because instead of water being formed and releasing this much energy, in order to break it down, it's going to give off that much energy. Okay, it's going to absorb that much energy. Okay, if we're looking at it in the reverse, we have to reverse the sign as well. So here's kind of my format for how I look at enthalpies of reaction. Okay, I like to just kind of go right underneath what's listed there, and I say sodium's enthalpy of reaction is 0, right? And 2 times 0 is still what? Still 0, right? So it's not changing anything there. Because my heat of formation is per mole, I have to pay attention to the coefficient that sits in front of it. All right, now water, it's supposed to be negative 286, but we're going to make it positive 286 because in my problem, it's on the reactants side, right? The negative 286 would work if it was on the product side, but it's not. And I have 2 moles of that substance. Okay? My sodium hydroxide, aqueous, has a value of negative 470. Can I keep that one negative? Yeah, because it's on the product side, and then H2 is still 0. All right, so I'm going to figure out what are those values, right? What do they come out to be? So let's calculate those values. Okay, so 286 times 2 is 572 plus 470 times 2 is negative 940. And so that gives me a value of negative 368 kilojoules per mole. Oh, not per mole. I don't know why I said that. Just regular kilojoules, okay? Because we accounted for the mole ratios here, so it's really not per mole. Okay? So there's our heat of formation for our total reaction, right? We're going to take the heat of formation for each individual compound and then be able to calculate the enthalpy that happened in that reaction. Okay, simple enough, right? No mini reactions, no changing. All we're doing is making sure that we're corresponding our compounds to the correct side of that equation. Yeah, Hope.
So anytime it's on the reaction side, it's going to have the opposite.
It's going to reverse the sign. Yep. Because the numbers they provided us here are given that it's a product, right? If the number that's provided is only allowed if it is a product, right? If it has been produced. All right, let's look at the next one. Cooper, we're just kind of jumping in here, so we've only done one slide, but if you need, okay. All right. Look for CH4 as a gas. Did anybody find it yet? Okay, I think it's organized by element. So carbon, CH4 as a gas is what? Negative 75. But is it going to be negative 75? It's going to be positive 75. And do I have to adjust anything for the moles? Nope, right? Because in our reaction, it called for 1 mole of that substance. Okay, next for O2. Before you even look it up, can you have a guess for what O2 is? 0, right? Because O2 is a diatomic. It's normally a gas. So you can confirm if you want, but it's a 0. All right, so I'm going to go plus 0 there. All right, CO2, I'm looking for carbon dioxide as a gas. Negative 393.5. No mole ratio there I have to consider, right? And then I'm looking for water as a liquid. H2O. There we go. Yep, negative 286, thank you. And I do have a mole ratio there I've got to pay attention to. So 2 times negative 286, right? I don't have to change the sign on water because it's already a product, okay? So I'm going to find out what that value is, and then we're going to add them all up, right? We just add them across from left to right. Mm-hmm. Yeah, because our value up here is given in kilojoules per mole, right? And so since we're not looking at enthalpy per mole anymore because we did our mole ratio, so it's just total kilojoules. Okay, so this would be the heat of formation of the reaction. Okay, simple enough, right? That's it. Okay, that's where we're going to stop.